Wonderful. So let me start with welcoming you here in our location. It's a great honor and pleasure to have so many sharp minds here talking and networking. And let me also start saying something on my person. My name is Treml. I'm the lead technological strategist and architect here in the public sector in Germany. And I'm happy that I got invited to spend some 15 minutes, which is really challenging, on future of technology. But every time I try to analyze the today's situation or even to look out in the future, it always helps me to get back a little bit in time, and I might start with telling you something about the building you are here. This was built as a hotel, to serve as a hotel at the end of the 19th century when Berlin was a booming city. And for example, if you would look out at the window at that time, or 20 years after the building was established, you would see a scene on the street like this. And the question is, in 1910 years, where's the car? There's one, quite hidden on the street there. If you take a photo also taken from under the linden 20 or 15 years later, the question would be like more, hey, where's the horse? And I took this as a picture for the paradigm shift we are just experiencing today. Looking back, we started with Microsoft running big server farms, big houses of servers some 20 years ago to host email services and so on. And then somehow on the way the word cloud was invented. And now, if you look at our figures published, quarterly results and so on, you see how much the cloud business is driving us and how much we are investing in it. And I see some parallels from this time 100 years ago roughly and today, because it's the same paradigm shift. You would never start building systems with computing power under your table. You would want, hopefully, to aim for big, scalable systems that can really do the immerse number crunching that is possible today in some of the aspects. So if you take this history and bring it a little bit together, you might say like we're moved from stream to electronics to digital, or we're just moving into this phase. And I just took one small example to show you how intense and massive this computing power, we already heard in the morning from my colleagues, is. We are running data center on a massive scale. It's like we're talking about 100 data centers worldwide. We're just opening 2 of them to be clustered in South Africa in the next month. And if you do a business like this, we are talking about like thousands of servers shipped into a data center on this planet every day. Talking about putting a power plant next to it, being it hydro, solar, or maybe some tidal waves that are used to produce energy. And let me take one example to show you the massive scale of that. For 7 months now, we have a service that is called genomics analysis as a service, running in our Azure data centers. And what it means is, if you are a university doing research, you want to do binomic analysis or sequencing, you don't have to build your own Cray or your own big data center. You just use ours for an hour or two, do your analysis. You just pay for this hour, and you get a scale of like 7,000 to 8,000 cores running and processing workload at the same time for this hour, and then you got your results and you are out. So my message to you at this point is leverage this massive scaling data center powers that are open to you. There are clearly defined APIs for the technical guys among you to be used. You just throw whatever workload to the data center, you get your strings, your results back, you put them in your application, and you do your business on top of that construction. Yeah? So this is my message to you at that point. And I think the genome sequencing, which is really hard number crunching, is a good example to show you the power of this network. Why are we talking about this now? We are talking about this now because out of three reasons. First, we do have a number of really powerful algorithms that are developed everywhere on this planet, being it in our data set with our engineers or in the industry or in the open source scene. We do have massive computer powers, as I just described to you, and we do have big data, and we also have the place to store them. Now, you all know the figures, how many pictures are uploaded per second to Facebook. You can imagine the waste amount of storage we are providing, because it's not a question if the storage you provide will be taken or used. It's just a question of when it will be full. It's a constant race against the time at that point. So out of these three reasons, the algorithm we have, or you can develop the massive compute power and the big data, and so different sources of data you can plug into and merge and use together. We are convinced that this is the time to use big data and artificial intelligence, or maybe I should say applied intelligence, to build a business upon that. If I'm showing you what we are doing today to take you on a journey then for tomorrow, it's important to say that if we are talking about our Azure data centers, which are hosting all this compute power and also maybe Office 365, we call them intelligent cloud. And why is there something like an intelligent edge there at the bottom? I just saw a drone standing outside there with some charging systems, and these two things, even if they don't look like at the first glance, they play very well together. So you would, for example, develop patterns and algorithms in your data center with massive number crunching, and then download these patterns you developed onto a drone or an edge device, which would be up to now, or like up to 2 or 3 years ago, which would be non-intelligent. For example, a drone would just take a picture and store it, or take a picture or a film, a video, and send it somewhere wirelessly. What we do now, and this is why we call it intelligent edge, so computing at the edge, is we develop the algorithms in the data center, and then we package them in containers like Docker containers and deploy them on thousands of drones at the same time. And what the drone is doing now is it's still filming, but it's processing the data locally and just sending back the results to the data center, not the full HD video material, but just the results. If you think about that for a second, I'm sure you find lots of business models to apply this logic. And what you need for this, you need a big data center in the back end where you can do deep learning, machine learning, and you need to really feed and train your algorithms to become really good, to detect holes in pipelines or whatever. We had a project for that with a PhD in London to detect illegal gold mines in Central Africa from just learning pictures. Is it just a settlement, or is it a settlement next to an illegal gold mine? So we train the systems, then we take it, package it, bring it to the devices like satellites. Not really yet, but that will come. But for example, drones is a good thing to imagine that, and then apply the intelligence locally. So we're going to come into some sharing. It's not client-server as it used to be in the 90s, for the old guys amongst you who still know this the idea of having a client and the server. It's more of like distributed computing with a big data center that starts the work first. And if you think about this kind of patterns and services you could apply, it comes down to 4 dimensions, so to speak. It's vision, speech, language, knowledge. And these are the 4 pillars we are now developing algorithms. For example, we recognize speech and to give it back. We had a couple of months ago, we had the break even when the machine was better in understanding simplified Chinese than a human being. Just a couple of months ago. Yeah? For vision, I had the example of a drone inspecting pipelines. Could also do emotion detection from people's faces, and whatever you can imagine on that. And in terms of knowledge, of course, we're talking about mining in big piles of documents and texts in an unstructured way. It could be a photo of a receipt, the same way it could be a Word document. You put it all together in a so-called data lake. Yeah? You throw your algorithms on it, and they will send you some structures or patterns or whatever they find out, or cross-connections, cross-references, and so on. This was not possible 20 years ago. I studied informatics and sociology in the middle of the 90s, and when I did some analysis, some multifactorial analysis of some data of like the 2,000 or whatever people I asked questions, it took me ages to script the question, and then after 7 or 8 hours I got back some result or an error message. So these 7 hours, they are now shrink to some milliseconds. And this is what you really have to understand what is happening. This is why we're talking about a paradigm shift from horses to cars, shift from a horsepower by horses to horsepower by combustion engines. We still call it horsepower because we're kind of traditional, I guess, as human beings. And it's hard for us to keep up with that speed. And the speed we are seeing, especially in developing large data centers and running them with energy. Of course, most of the amount is renewable energy these days, and providing this service 24 hours, 7 days a week for you to build reliable services on that is a massive effort. But besides the technical dimension, it also has a psychological, or maybe I should call it philosophical dimension. And of course, we are eager to think about the ethical and philosophical dimensions of this immense computing power that sits within AI, within artificial or applied intelligence. And our goal and our outspoken goal is really to amplify human ingenuity and find rules and regulations, what to do and where to apply this massive power we're having on our fingertips. Everybody of you has on your fingertips. It's really easy to set up an account and feed whatever with pictures and get some results back. So this is the state we're having today. This is open for everybody for you, and I'm sure when in the following panel discussions we will feel you will have some business cases or you'll get some ideas how to apply that to a business you want to set up. If we look into I think I've got some minutes left. If I want to make 2 more points, if we look what we are researching on these days is, for example, I brought you this picture. It's about the size of a standard shipping container. And we were sinking it a couple of weeks ago off the shore of Scotland. And this thing has 864 servers, 26 petabyte of storage space, and it's run by energy produced by the tide. And sitting 20-40 meters under the sea level. And if you want to look for it, it's called NATECH, N-A-T-E-C-H. If you look for it with your search engine of your trust, you'll find it very fast. And it's Bing, isn't it? And they also, the engineering colleagues were so cute to put a webcam into it, so you can see the fishes swimming by next to the cable where this undersea data center, which is in experimental state definitely, is connected to the power tidal power and to the data. So one more input I'd like to give you within my 15 minutes is any idea what this is? Yes, you built one already probably. Yeah, this is a quantum computing device, and we've been talking about quantum computing for some decades already, but now is the time where it gets really concrete and really physical. We have one built in Santa Barbara. We're just building two in Europe, one in Copenhagen and one in Amsterdam. And yes, the building is already there. The stuff gets into it. It's starting. It's a challenge because it's for us humans and also for me as an informatic guy. It's hard to understand what quantum electronics means. If you imagine you have two electrons moving at the same time and with 40 kilometers distance between, ooh, wow. Yeah? But that's the reality these days. The challenge is to cool these machines. You need a lot of energy for that and to keep this electron stable. But yes, it is there. And what we think we will use it for is, for example, let me just take one of them, like the nitrogen fixationer. Nitrogen fixationer is producing fertilizer, for example, or other base materials for chemical industry. Nitrogen fixation uses 4 to 5% of world energy because it's a 100-year-old system with a lot of pressure and heating you have to imply there, so it's very energy intense. So we are looking for ways to find new ways, lower pressure, lower temperature, whatever, like plants. Every green plant on the floor or on the ground can produce nitrogen. So we want to use the quantum computing to simulate processes taking place in roots, in plants, and whatever, to find more effective ways. And also that, it's future, it's near-time future. We already have the first physical quantum computing devices, going to build more, but to prepare for that age of massive quantum computing power, my tip for you is get familiar with our quantum development kit. We have a new programming language for that, which is called Q#, and just simulate it. You can simulate it on your local machine with some so-called 20 qubits. It's not a bit anymore, but a qubit. But you can also use Azure data centers to simulate higher workloads and get ready for the time being in 2-3 years when quantum computing will be more or less on the way to being a commodity. So you find more information here on microsoft.com/quantum. And my last slide on that, for all the Linux lovers among you, we love Linux too. We are the biggest crowd of contributors to Linux on this planet, with a couple of thousand plus developers contributing code every day, maintaining it. Yeah? And now we also have, with GitHub, a really great repository to share and provide this knowledge and open source more and more of this new technology, like Q#, open source, all the new blockchain projects we are doing, open sourced. So this is my last slide. So thank you. So far, I hope I filled the time with some good inspirations and some impulses for the panel afterwards.